We're continuing with the second movie in chapter 4. We're going to start here with the counterbore requirements. A counterbore is a stepped increase in hole diameter like we're showing right here. The bottom is perpendicular to the axis. The bottom of this hole is perpendicular to the axis, specified providing a hole diameter, which is the hole diameter here, the 250, the counterbore diameter, and the depth, and the fillet radius. The fillet radius would be this corner radius right here at the bottom. The remaining material may be dimensioned for depth. That's where you're taking this thickness here that's left after you could make the counterbore and dimension that. And it's commonly used, as shown in here, to recess the head of a fastener. So you need hole diameter, hole depth, when that's required, counterbore diameter and depth, and you also need the fillet radius. A countersink. A countersink is an angular increase in hole size. It's specified by providing the hole diameter, countersink diameter, this is the breakout diameter at the top, and the countersink angle. It's commonly used to recess fastener heads on flathead screws and break sharp edges of holes. Okay, so in some cases you just want a smaller chamfer here just to break the sharp edge, just to help lead in the fastener, if you will, on a threaded hole. Or you could use it to recess a flathead screw. Here's another type of feature. It's called a spot face. It's very similar to a counterbore, but really it's not. It's just really to give you a cleanup where you can use a washer. You have a flat bearing surface for your fastener. The minimum information is the hole diameter and the spot face diameter. Now the spot face diameter really just goes to the flat. I mean, if you have a corner radius here, that corner radius is in addition to the spot face diameter. Okay, so in this case, the spot face diameter is this 750 thousandths, and then it's actually larger. The overall diameter is actually larger because it takes care of this radius. Okay, so no specified depth requires adequate depth to create a flat surface. So the most part, these are specified like this. We have a applied dimension to the thickness that's remaining after you put the spot face in. And when the fillet corner radius is specified, it does not include this flat diameter. Okay, so that's a spot face. Okay, angles. Never implied for models between features and must be queried if dimensions are not shown. Perpendicular surfaces in orthographic views implied to be at 90 degrees with respect to each other. Dimensioned by showing degree features that create it, or by dimensioning the vertices. Let's look at some examples here. Okay, in this case we have an angle surface right here. We have 5 degrees, and then we also have a dimension to one of the vertices. Okay, so one corner of the angled surface is dimensioned. The second corner of the angled surface is located by the intersection of this 5 degree from there. So you need one of these vertices named, and you need the angle named. Now, when we're talking about angle specification notation, you got 30 degrees is written like this. If you're writing it in minutes and seconds, this is what it would look like. But for the most part, most drawings use decimals. Okay. The center of dimension line arc at the vertex of the angle, so that's here. This dimension comes back to the vertex of the angle, and the extension lines intersect at the vertex of the angle, right there. So that's how we dimension an angle. Now, limits of size. All dimensions excluding basics must include a tolerance. Yeah, we talked about this extensively in the working drawings. The amount of variation is allowed, and that's what's specified as a tolerance. The size dimension tolerances are applied to dimensions or the feature. Maximum and minimum allowable sizes are based upon applicable size tolerances or limit dimensions. Okay, let's look at some examples here. Okay, and here we're using limit dimensions. Okay, in limit dimensions, we're stating the upper limit and the lower limit of the tolerances that are acceptable. In this case, the maximum limit is always written above the minimum when both are shown, and the minimum limit precedes larger in a note and separated by a dash. Okay, so if you're putting it in a note, you're going to put the minimum dimension first, the dash, and then the maximum. If you're going to show it on the field of the drawing, like this here, between a dimension line, you're going to put the larger dimension on top and the smaller dimension on bottom. And really, if it's a diameter, you need to include the diametrical signal. Okay, now those are limit dimensions. These are plus or minus tolerances, okay? In this case, the tolerance is stated by a nominal value with a plus and a minus. If we have plus and minus values, that is a bilateral tolerance. If one of the values is 0, we have a unilateral tolerance, okay? So the tolerance is greater in one direction than the other. In this manner, you're designing a plug here that fits into the slot. So bilateral tolerance allows variation in both directions. They may be equal or different. Equal bilateral tolerances are a special case. Now, single limit dimensions. Now, limit dimensions are only acceptable when a second limit controlled by part geometry. So in this case, our radius is 0.03 max. Our minimum radius would have to be a sharp corner or 0. So what this means, as long as the radius here is somewhere between 0 and 0.03, then the part is acceptable. That is a single limit dimension. That comes with a max or a min type, just like we're shown right here. Calculations of size tolerances. Standard tables for tolerances between fits. These are talking about fits right now. When you're talking about fits, you're talking about a male part and a female part. It's usually a hole and a shaft. And the fit is the relative tolerances of those two parts and how the parts fit together. We did this extensively in GD&T, and I think we did it in machine design too, where we went through these things and we calculated everything, but we're not going to do that in this class. We're just going to talk about these fits in general terms. Okay, so the standard classes of fits would be the RC, running and sliding clearance fits. When you put these two parts together, it's for like a hinge or something like that where the wheel has to spin on the shaft. Okay, you need clearance. And that's a running and sliding clearance fit, okay, in which case the hole is always bigger than the shaft because you're talking about tolerance conditions on both the hole and the shaft. Okay, so a LC is a location clearance fit. And this, what you're trying to accomplish with a location clearance fit is you're trying to assemble two parts together and they're going to have to fit fairly tight. Okay, so the parts aren't necessarily going to have relative motion to each other like the hinge or the wheel spinning on a shaft like the RC, so it's a little bit tighter fit. LT is where you have a transition fit. Okay, the tolerances of the hole in the shaft are such that they may be clearance at one end of the tolerance and they may be interference at the other end of the tolerance. And since you're just trying to locate these parts and put them together, then that should be acceptable for that type of fit. And then there's the locational interference fits. Those are the ones where, regardless of what end of the tolerance range that you're on, you're going to have interference between the hole and the shaft. And those are designed specifically to locate something really precisely and be able to put it together where it's going to stay. Now, force fits, on the other hand, is a very heavy interference fit. And those fits in manufacturing are typically achieved by freezing the shaft and then heating up the wheel to use the coefficient of thermal expansion to your advantage and cause a situation where the parts will go together almost like a clearance fit, but after they have achieved steady state in terms of the temperature of the parts, then you'll have a interference or force fits. I'm going to talk just a little bit more about this in the next movie. Thank you.